So welcome again, everybody. So today we're going to work through worksheet 15, which is dealing with the phase plane portrait. So the plan is we got some work on nullclines that we're going to talk about today. There's a separate reading document for that, since there's no information in the notes on DiffyQs about nullclines. So here's a link to a different textbook where they've got some information about nullclines. They've got a bunch of examples in those notes. And here are the solutions to those examples. So if you want some extra practice on nullclines beyond what we talk about today, check out these documents in Canvas. And then on Thursday, we'll be working more with phase plane and phase plane equations. And I have a separate set of notes for that over here for what we're going to talk about on Thursday. And here are the two links for the worksheets we'll be doing this week. And so otherwise, the plan for this week is you've got a homework assignment that is due next Thursday. So there's no collab or written homework due this week. And there's a quiz before our next class on Thursday. So any kind of general questions about the plan this week? Okay, well then let's get started. I have started grading your exams. I was hoping to get through them yesterday. I was not really able to focus, so I'll finish them up and definitely get them back to you on Thursday this week. Okay, so here is worksheet 15, which is dealing with what are called phase plane portraits. So I want to start just showing how we can plot some of these things in Colab, and then discuss how we can kind of look for where some interesting properties might be located so that we get a sense of where we might want to tell Colab to zoom in around the phase plane so that we can pick up on some interesting properties like the behavior of equilibrium. So we're going to kind of balance things a little bit today, doing some stuff on Colab and then doing some old-fashioned analysis by hand and comparing the two. So to get started, I just want to walk through the process of creating what's called a phase portrait in Colab. And so this function, phase portrait, and another one that we're going to use in a second, these are both located in the ODE tools module that you downloaded earlier this semester. So you don't need to re-download that file. These things should already be in there. All you'll need to do is set the file path to wherever you saved ODE tools. So if you're working in Colab, we want to first mount all of our drive in our active session. And the goal here, again, is we're working with systems of differential equations. So we started talking about this before the exam. So recall that when we're working with a system of differential equations, we have different planes that we can look at the solutions. I can look at the solution of x versus time. I can look at the solution of y versus time. And then we can look at the relation of x and y. And then for us, we were looking at rabbits and foxes and looking at a predator-prey model. And ultimately, when you're working with these systems, what we tend to do is plot things in the phase plane where we compare rabbits and foxes to each other, and we indicate time by putting arrows on the solutions to indicate which direction we're rotating along those solutions. So I've just loaded up my drive, and here's my file path. I'm not using Jupyter, so I will skip over this. And so the function that we're going to be using, this is what's called phase portrait. And it's in this ODE tools module. So if I hit play here, I hopefully don't get an error. I didn't. If you did get an error, this is probably because of your file path. And so the function is phase portrait. And you could see it down here. And there's going to be three things that we need to define before we run that function. And that's going to be what is our range of x values on the horizontal axis, what's our range of y values on the vertical axis, and then what is the system of differential equations. So here, our function f is actually going to be a vector that contains two differential equations. So up here, we're going to define our range of values for x and y as vectors. So that's why I've imported NumPy in this code cell. And I'm going to plot x, x being our rabbits in this case. So we're going to work with the same rabbit and fox differential equation over here. So I'm going to plot rabbits from 0 to 5, and I'm going to plot foxes from 0 to 5. So that is both of these things over here. So this means where do we start? This means where do we end? And this is telling how many values am I going to pick between 0 and 5. Then down here, the two places where we're going to need to enter our functions are going to be right down here in the return section of the function. So first, I enter the differential equation for x. So in this case, I've got 3 times x minus 1.4 times x times y. So r is my x in this case, and f is my y. And then down here, I'm just entering the differential equation for f. And that's all I need to enter is what is my range of x and y values, what is the system of differential equations, and now I run phase, portrait, plot. And we get this phase portrait that we were working with last time. So again, you can think about this as this like this cyclical behavior between rabbits and foxes. As the rabbit population goes up, that affects the foxes. As the fox population goes up or down, that affects the rabbits. Okay, so any questions about running this phase portrait function in Colab? You're welcome to raise hands or just unmute yourself. Is anybody in our classroom? No. Okay. Yeah, I'm remembering the black vortex of faces here. I won't give you all a hard time because I get to see you all the time. So that's fine if you want to take a day off from looking at me. Okay, so next up is a different function, which is called plot phase solution. So here, if I have some initial population of rabbits and some initial population of foxes, then I might want to know what are going to be the dynamics as time goes on, right? Let me plot the solution that passes through those initial conditions. So here we can just see the full-on phase plane. But if I want to take a look at one particular solution, there's just one more set of, or two more inputs that I need to enter. And one of them is the span of time that we're going to plot this solution. What is our initial x value and what is our initial y value? The x and the y and the f, these are all the same as what we entered previously. So I'm not going to even run this code cell over here. This is just here in case I didn't run this already. But we're going to use the same window for x and y. We have the same system of differential equations. And so in any of the problems that you need to do with this, I'm not going to ask you to like figure out a reasonable time span. So we're just going to go like from 0 to 50, picking 200 time in between. That should be sufficient. But what you will need to tweak is what the initial conditions are. So let's just say we had like 2, which means like 200 rabbits, and 3, meaning 30 foxes. And I want to see what that solution looks like I first need to define these values for the time and the initial values. This is a different function, so I need to import this second function now, but it's from the same module, so I don't need to set a different file path, and then I just run this. Now we can see the solution that we started with at time 2, 3 was this red dot over here. And these arrows give us an indication of which direction we're rotating around this curve. So last time we were kind of looking at things in 3-dimensional space and projecting into these different planes. But for today and for pretty much the rest of our time in working with systems, we're really just going to be focused on the phase plane. Okay, any questions? Yeah, Jeremy.
Yeah, I was just trying to think about like what the difference is between this and like just plotting a solution curve. If there's like how to think about them differently.
Yeah, so actually on Thursday, we'll talk about how I could find a solution for this just analytically, right? Without a picture in the background, just working with the equations. How can we find what are called, phase plane equations and solutions? So we'll get into kind of how we can find formulas for these things. But for now, you just might want to think about, we're just doing this a little bit informally by plotting a bunch of vectors, and then kind of like how we started working with one ODE, then we can just kind of follow the arrows. All of these arrows should be more or less tangent to this curve at all values of time. So right now in the background, Python is doing some stuff and solving this for us. But on Thursday, we'll kind of learn how to do that ourselves. Yeah, if that didn't answer your question, just let me know.
Thank you. Yeah.
Okay.
I don't have a quick question.
Sure.
So I'm just a little confused what the blue box in the red circle is.
Yeah, very good question. There is no significance to that whatsoever, other than the red dot is the initial value. So that's where we started. That's the 2, 3. I don't know what that blue rectangle is doing. You can kind of disregard that. Okay, so more or less for the next, more or less for the kind of rest of this time, let's think about how we can uncover some interesting features in these phase planes. So for example, here, probably the interesting feature is this equilibrium that's like, right inside the center point of all of these cycles. And so if I were plotting this in Python, I need to tell Python where these interesting features are, right? This is at the point, it's roughly at 1, 2, but there could be other equilibrium in other places in the phase plane, right? And we might be missing them here. So we want to talk about how we can do some analysis to identify where these interesting points might be and how we might be able to understand the dynamics, just having kind of an outline of this phase plane without having all of the arrows filled in for us. Okay, so let's kind of just start with this differential equation over here. And I think I'm going to just switch over to my iPad so I can draw on these. Yes, hello, all of you black screens. Okay, so hopefully, can you all see this? I'll take that as a good sign. Yeah, thank you. Okay, so this is just a static PDF, but I want to mark it up. So here we are. Our differential equation is dx dt is y minus x, and dy dt is minus y. And we want to sketch some vectors here. So, for example, let's say I want to think about what is happening at the point 1, 0. Oops. So when x is 1 and y is 0. So I can use these differential equations to figure out, okay, dx dt, that is going to be 0 minus 1, which is minus 1. And the y dt would be minus 0, which is 0. So what would this vector look like in the phase plane that I'm going to draw at this point right here? I'm still allowed to ask questions, I think. So we've got the point 1, 0. We found out that the slope in the x direction is minus 1, and the slope in the y direction is 0. So feel free to chat it in. Just want to make sure everybody is following along. Did you guys miss the question? What would the vector that I'm going to draw at 1, 0 look like if we figured out that dx dt is minus 1 and dy dt is 1? Thank you. Very nice picture, Stephen. I have no idea how you got an arrow in there, but that is correct. It's going to be an arrow that points directly to the left. And we can see that because dx dt is telling us what's the horizontal component, and dy dt is telling us what the vertical component is. So this means because it's negative, we're going to go directly to the left. And this means there's no vertical component. So it looks like this. Let's see. Alt 27. Thank you. Yeah, so that's going to go directly to the left. Any questions? Okay, so what I'd like to do is have you fill in a few more vectors. So I'm going to just give you a couple minutes. I'd like you to fill, you don't need to fill all of these out, but I might just suggest picking a couple of different values. And hopefully the idea here is that we're going to pick up on some patterns as we're plotting these vectors. And we'll try and talk about what those patterns are. But I am going to give you a couple of minutes to work on this, and I'm just going to pause the video and just mute myself for a second. And it's 9:49. So let's come back at 9. We'll give this like 4 minutes. So we'll come back at like 9:53. We're not going anywhere, but I'll kind of unmute things in 4 minutes and we can kind of share our thoughts. Okay. Any questions about what the task is here? Okay, awesome. Okay, we are back recording here. So does anybody notice any kind of nice patterns that you picked up on as you were graphing some of these vectors?
The x-axis, I think it like points into the origin point.
Yeah, so on the x-axis, and I'll share my screen in a second. I'm keeping mine hidden on purpose. But on the x-axis, the vectors are pointing towards the origin, right? And in this case, that means they're pointing straight horizontally, right, to the left or to the right. And how do we know they're pointing horizontally? Like what was it about the calculations that told you they were pointing strictly horizontally?
Whenever y is 0, then y prime is 0.
Yep, perfect, right? So at those points on the x-axis, dy dt is equal to 0 for all of those coordinates because they all have a y value, which is 0. Awesome. Any other patterns that people picked up on? So similar to how there are some vectors that we saw pointed strictly horizontally everywhere. Did anybody notice a pattern in vectors that were pointing directly up or down? And what sorts of points gave us vectors in the phase plane that only had a vertical component?
Well, if y is positive, then dy dt is negative, and then also if y is negative, then dy dt is positive.
So if y is positive, dy dt is negative, and if y is negative, dy dt is positive. Okay, and let me share some of these observations. Okay, so down here I have the first observation here that on the x-axis vectors are pointing horizontally left or right, and that's because dy dt is equal to 0 for all of those points. Looking at this differential equation, in particular this one over here, we can see that yes, whenever y is positive, dy dt is negative. Whenever y is negative, dy dt is going to be positive. So that is telling me that all of these vectors are pointing down since y is bigger than 0, right? Dy dt is negative. And all of these vectors, I haven't drawn that many of them. Over here, these are going to point up when y is less than 0, since dy dt is going to be positive for all of those. Yeah, this is great. These are exactly the types of observations that are really helpful to hone in on. So one thing that we kind of haven't mentioned, but I'll highlight them in my vector field, is we have a group of vectors, right, which have strictly pointing up or down. And what do you think these vectors all have in common? So how can I identify places in the phase plane where the vectors are just going to point directly up or down?
Is that just when y equals x?
That's right. So all of these vectors here, what they have in common is dx dt is equal to 0, right? And here dx dt is our measurement of the horizontal direction of the vector. So all of these vectors have dx dt equals 0. And we can see from this equation that that's going to occur when y is equal to x. So I have this whole line of vectors that are either pointing directly up or directly down. So this, as well as this line over here, these are really special lines. Just kind of mark this over here, because all of the vectors on this line are horizontal, whereas all of the vectors on this line in red are vertical. And where these two lines intersect, I'm going to put a big point, which is like right here. What do you think is significant about the point where they intersect? So what do we call these points? Say at the origin where dx dt is 0 and dy dt is 0. That was a special type of point. Do you remember what we called those? Chat. Equilibrium, correct. That is a special point, which is an equilibrium. And so equilibrium, we represent in the phase plane as just a single dot, right? There's no horizontal component or vertical component. If I started at the origin, I'm going to stay there for all time. And then the question might be, is this equilibrium stable or unstable? What do people think about that? So if I start at a point close to it, what direction am I going to head? Towards the equilibrium, away from the equilibrium, sometimes towards it, sometimes away from it. Yeah, this is going to be a stable equilibrium. And I think I've got the full, yeah. So here's the, oh no, I don't have it here. Got it here. It's kind of the full slope field for this system of differential equations. And so now you can see maybe it gets a little bit hidden in the midst of all of this noise. But here you can see all of these vectors that are pointing downward on this line y equals x, or upward. And similarly, we've got these vectors over here that are going directly in on this line y equals 0. And so these two lines, what are called isoclines. And so an isocline is a line through the phase plane where all of the vectors have the same slope. We'll see some other examples of isoclines besides what we're going to take a look at today with x and y-nullclines shortly. So again, on that phase plane, since on that line y equals 0, all of the vectors have the same slope, meaning those vectors all had slope 0. They were horizontal. And then on the line y equals x, all of those vectors were vertical, so they all have the same slope, which is like an undefined infinite slope. So we're going to focus today on two isoclines and what they tell us about the long-term dynamics of a system of differential equations. So one is going to be an x-nullcline. And the x-nullcline is referring to the fact that the vector is null in the x direction. So these vectors are going to point straight up or down. And these were located on the line y equals x on the previous example that we took a look at. And a y-nullcline are going to be lines where all of the vectors on that line have no vertical direction, and they just point directly to the left or to the right. And that was the line y equals 0 for us. And so I just want to point out, and it probably looks a little bit nicer in the Colab document, that what I did here to add these two lines to this phase plane is I created the phase plane portrait, and then I just added these two lines separately. So here is the line y equals x, and here is the horizontal line y equals 0. Any questions? Okay, so let me just set up a new page here. And let's think about how we could identify these just from the system of equations. So in this case, we had dx dt was y minus x, and dy dt was equal to minus y. So for an x-nullcline, how we identify these is we set dx dt equal to 0 and solve. And there may be more than one x-nullcline or y-nullcline, so we want to find them all. In this case, we just have one of each. So in this case, we're going to take dx dt. Oops. Set it equal to 0 and solve. So we get the solution y equals x. So that gives us one x-nullcline. And I'm going to start to sketch this out in the phase plane. So I just drew my line y equals x. Any questions so far? Okay, then we find the y-nullcline similarly. Let me just write out the step here where we would set dy dt equal to 0 and solve. In this case, we've got dy dt is equal to minus y equals 0, and that has a solution y equals 0. So we did talk a little bit before the exam about finding equilibrium, and we'll talk about this more next time, and about how we need to solve a system of equations. We need dx and dy dt to be 0 simultaneously. So for the nullclines, we're just taking those one by one, just looking at them separately. Okay. And then the next thing that's going to be useful to do is going to be to actually indicate whether the vectors point up or down or left or right on these nullclines. So right now, I know that all of the vectors on the red line are horizontal. But I'd like to know, are they pointing to the left or to the right? And that depends. Sometimes they point to the left and sometimes they point to the right. So the next thing that we wanted to do is determine directions. Let's say if we want to determine the direction on the y-nullcline, we're going to need to use the equation for dx dt to identify these. So we're going to substitute, in this case, the value of the nullcline y equals 0 into the formula for dx dt. So what I did is I just took our nullcline, plugged it into the equation for dx dt. And now we simplify that. And now we just think about the signs. For what values are the vectors going to be positive versus negative? So we're going to determine conditions on when dx dt is positive and when dx dt is negative. So in this case, we have dx dt equals minus x. So we can see that dx dt is going to be positive when x is less than 0, and dx dt is going to be negative when x is greater than 0. So again, remember dx dt being positive means we point to the right, and dx dt being negative means we point to the left. So to come back to our vector field, that means when x is positive, these vectors are pointing to the left. When x is negative, the vectors point to the right. So that gives us that picture along that nullcline. Any questions? Okay, then we do the same thing on the y-nullcline. We're going to determine, or excuse me, on the x-nullcline. We're going to determine directions. And in this case, they're either going to be up or down on the x-nullcline. And keep in mind, we very well may have more than one in a lot of situations. So we might need to do this a couple of times. But in this case, we have one nullcline, one x-nullcline. And we've got the equation for dy dt. So let me just say, here, the plan is going to be to substitute the conditions for the x-nullclines in this case, the y dt was minus y, and then we're going to plug in our nullcline, which really doesn't do all that much for us. Plugging in y equals x would just give us like a minus x over here anyway. And using either of these conditions, so I could actually work with this one since this was the observation we made earlier, then we determine conditions for when dy dt is positive or negative. Which we've made already. We said that dy dt is going to be positive when y is less than 0, and it's going to be negative when y is bigger than 0. So now I'm going to take these conditions, and again, these just tell me what happens on that, in this case, x-nullcline. So on the x-nullcline that's in blue, when y is positive, they point down. And when y is negative, they point up. Okay. Any questions about that?
So is this like just kind of like if you had multiple phase lines? Something like that? Like you just treat each nullcline as a phase line?
So with phase lines, right, the slopes were different on different places. Yeah, I suppose you can think about it like that. It's a little bit more complicated now, right? Because we've got this interrelatedness between X and Y. But I'll say that we can use these nullclines to understand the full phase plane. So just by plotting these lines right now, it's going to give me an idea of what's happening in the full phase plane. So I think in that sense, yeah, it's pretty similar that with slope fields for very special differential equations, for autonomous differential equations, if we understand what the phase line looks like, then we know what the full slope field looks like. And so it's a similar idea here. Yeah. And so what this does is it divides the phase plane up into 4 different regions in this case. I'll label them. So here's like region 1 would be like all this stuff over here. I don't want those lines here. Region 2 would be over here. I'm just labeling them randomly. The numbers are not that significant. Here's 3 and here's 4. And so in region 1, it's trapped between a nullcline that's pointing in this direction and a nullcline that's pointing in that direction. So this tells me that all of the vectors in region 1 are pointing down and to the left. So the exact slope, not that important, but at least I can indicate they're pointing down and to the left. And in the second region over here, they're doing the, excuse me, I said down and to the left, but these are pointing to the right, aren't they? Sorry. So all of these vectors point down into the right in region 1. In region 2, they're pointing down and to the left. So all of these vectors would look like this. In region 3, they're now pointing up over here and to the left over here. So these all point up and to the left. And in region 4, it's up and to the right. And so here I do get the full picture of what's happening in the phase plane, at least like informally. We're missing some of the details. But now I know kind of where I would want to zoom in on this phase plane, and I can get a more complete picture by using Python or something like that. But Python doesn't tell us where these interesting features are. So we need to kind of track these down by hand. But now this gives me an indication that right here at the origin, this equilibrium is indeed stable, because no matter where we are, everything is going to approach. If I start close to that equilibrium, right, all of these arrows are pointing back in towards the equilibrium. Okay, any questions? And this was what we more or less had over here. And so here again, you can see we have these 4 regions. In this region, things are generally going down and to the right. Here they're going down and to the left. Here they're generally going up and to the left, and then up and to the right. So it kind of matches our analysis that we got with the phase, with the nullclines. Okay, so these are one of these things. I suspect X and Y nullclines. I'm not getting too many questions, which is good, but I think oftentimes what happens with these is that you run into the questions when you start to work on these problems. So I want to give some time while we're together for you to work on one of them, and then let me know what sorts of questions or where you might be running into some problems in this process. So here we're going to work with this rabbit fox population, and we kind of have an idea of what this looks like already. But let's imagine we didn't have the phase plane portrait for this. So the idea here is let's find the X and the Y nullclines, and let's plot those nullclines and the direction on those nullclines. So what I don't want is a picture like, the full slope field. I'm looking for a picture more like this over here, where we've identified nullclines, and from those nullclines, we then find the direction on those nullclines. Okay, so I will give you some time to work on this. This might take a little bit of time, but the idea is to find the X nullclines, and there may be more than one of them, to find the Y nullclines, and then determine the directions on those nullclines, so we get kind of a rough sketch of the phase plane. But I want you to try these on your own rather than me walk through them, and then we'll go through them together. So if you do run into some questions, you're welcome to raise your hand, to speak up, or to chat them in. I'll stick around here, but I'll just give you some time to work on these on your own. Yes, the equations would be useful. Here they are. My hint here is that you should find 2 X nullclines and 2 Y nullclines in this case. And just to give you a little gentle push in the right direction, the idea here is you're trying to figure out for what values of X and Y is dx dt equal to 0. And so these nullclines, they could be constants, or they could be an equation like y equals x. If it helps to kind of check your thinking as you're going along, I'm just plotting the x-nullclines at this point without any vectors on them yet. So if you have any questions on what I've done so far, feel free to chat them in or unmute yourself. Okay, so I've got the nullclines for X, the x-nullclines drawn in red and the y-nullclines drawn in blue. There are two of each. So any questions about that so far? Okay. So then in order to determine the directions, right, if I just take this y-nullcline that we just found, it has no y direction. So we want to figure out which way does it point in the x direction, right? I take my condition that I found for x and I plug it in to the equation for dx dt. So I've got 3 times 1.25 minus 1.4 times 1.25 times y, right? So I'm just plugging in 1.25 for x in the equation for dx dt. And then we simplify this. What do we get? It simplifies to 3.75 minus 1.75 y. And so here, what we can see is that if y is bigger than 2.14, then the x dt is going to be negative. And if y is less than 2.14, the x dt is positive. And again, I get that really by thinking about this equation. I can figure out when that equation is equal to 0 and then test the value to the left or to the right to determine, when is that going to be positive and when is that going to be negative. So now we were working on this line, x equals 1.25, and determining whether they point to the left or the right. And that depends on whether or not y is bigger than or equal to 2.14. So when I'm less than it, we are pointing to the right. So we should be looking like this. And when we're bigger than 2.14, that's when the direction changes to the left. Any questions? Okay, so then on the other y-nullcline, which was y equals 0, we check the signs of dx dt. So here dx dt is going to be 3 times 0 minus 1.4. Oh, sorry, this is y is equal to 0. So it's going to be 3 times x minus 1.4x times 0, right? So now I'm plugging in the condition that y is equal to 0 into the equation for dx dt. And that simplifies to 3x. So here we can see that when x is bigger than 0, dx dt is going to be bigger than 0. And when x is less than 0, dx dt is also going to be less than 0. Okay, so here we were at the line y equals 0. And now what we're saying is that when x is positive, these are pointing directly to the right. And when x was negative, these are pointing directly to the left. Okay, everybody with me? Thumbs up, thumbs down. If you want me to talk about something, repeat it. Okay. Okay, so then we'll do the same for the x-nullclines. We had 2, x is equal to 0. And I'm approximating that. Y was approximately 2.14. I think more specifically, it was 3 divided by 1.4.
Just 15/7.
Sorry?
Sorry, it was 15/7 is what it ended up being. If you just wanted an exact fraction.
I think I got 3 over
That's-
1.4 over here for that one.
Right, which is just 15/7.
Yeah, okay, yeah. Yeah, and so now we check the signs of dy dt. So that was minus y plus 0.8xy, using each of these conditions. So for x equals 0, right, that just simplifies to minus y. And so we can see that dy dt is positive. Vectors are going to point up when y is less than 0, and dy dt is less than 0. Vectors are going to point down when y is bigger than 0. So over here, they're pointing up and up. I think that's what I said. They point up when y is less than 0. Yep. And then they're going to point down over here. Any questions? Okay, and then for y is equal to 2.14-ish, here we've got dy dt. I'll write it like this, is minus 3 over 1.4 plus 0.8 times x times 3 over 1.4. And we can set that equal to 0, first of all, to figure out when that's going to be 0. And that should occur when x is equal to 1.25. And here, checking values of x, we can see that when x is bigger than 1.25, dy dt is positive. And dy dt is going to be negative. We'll get downward pointing arrows when x is less than 1.25. So we can come back over here and we get upward arrows when x is bigger than 1.25, and we get downward arrows when x is less than that. So this would kind of be the kind of outline of the slope field that we get from just looking at the x and the y nullclines. How did everybody do? Where did anybody have any trouble or any questions along the way? Okay, so now the question might be, where are our equilibrium, and are those equilibriums stable, unstable, semi-stable? So where are the equilibrium located for this example? How can we identify where we've got equilibrium?
Would it be where the nullclines intersect?
It's going to be where the nullclines intersect. So that's right. So here is an equilibrium. Here is an equilibrium. These other points here and here, we are getting an intersection of nullclines, but these are not equilibrium. And what's the difference between the 2 points that I've marked here and over here, between these points over here and over here?
The first 2 points. Oh, someone else already answered.
Okay.
Oh, wait.
No,
Well, the first 2 points are just both dx dt and dy dt equals 0.
yeah. So what's important here is we're looking for intersections of different types of nullclines. So if I have a red nullcline, in this case, this is an x-nullcline intersecting with another x-nullcline, this is just telling me dx dt is equal to 0, but there is a vertical component here, right? So this is not in equilibrium because dy dt is not 0. So we're only going to get simultaneously dx dt and dy dt 0 when we're looking at the intersections of nullclines of different types. So I need an x-nullcline to intersect with a y-nullcline. So we've got an equilibrium. One of them is at the origin, and the other one is at 1.25, 2.14. And now I can use the fact that this divides the region up into areas where the vectors don't change directions. So in this region over here, right, the vectors point up and to the left. So that's why I've drawn this green vector over here. And I'm just going to draw these out. So in this case, these are pointing down and to the left. Let me get rid of this. So these are all pointing down and to the left over here and over here. These now point down and to the right, up and to the right. These are pointing up and to the left. And these are up and to the right. So if I zoom in close to this equilibrium over here, right? We're seeing that cycle of going up and to the left, down and to the left, down and to the right, up and to the right, that we saw earlier with that equilibrium. So we said something like this was stable equilibrium because points that start near that equilibrium stay near that equilibrium. And so I see there's a comment about what's going on at 0. Oh, I see. Sorry, I missed the question here. Anything special about the box that's made by the nullclines? Just in the sense that it's splitting up the region into areas where the vectors have the same general shape. So for like each of those regions that get blocked off by nullclines, we can determine the directions by looking at the directions of the boundaries of that region. And so the equilibrium at 0, 0 is not going to be stable. That's right, because we can see if I start here, we move away. If I start here, we move away. But over here, if I start on this axis, okay, regardless of what it means to have negative amounts of these populations, I do head towards the equilibrium here. And I do head towards the equilibrium if I start above it on the y-axis. So what I can see at 0, 0 is that there are some conditions that will move away from it. There are some initial conditions that will head towards it. So in this case, we call this a semi-stable equilibrium. We also might call this a saddle point. So that means some directions are unstable and some directions are stable. And let me take a look at the, yeah. So over here, I've plotted the kind of full slope field, and I added my nullclines here. I think I missed a nullcline, didn't I? Which one did I miss? The origin, I see. So I see. I think I just ignored what was going on at 0, 0. I see. This got cut off. That was my problem. Let me open up. Yeah, just trying to show the full picture. So if you run these lines of code, and over here, what I've done is I've just added a horizontal line at y equals 3 over 1.4, a vertical line at x equals 0, a horizontal line at y equals 0, and a vertical line at x equals 5/4 at 1.25. And that gave us this picture over here. So we can see kind of the swirly thing going on around this equilibrium. We can see the semi-stable equilibrium at the origin. And we kind of get the fact that in these other regions that are being boxed off, these vectors all have the same general direction in those regions. Okay, so we've got 1 minute left. Well, there's one more problem on this, but I think it makes sense to, well, since we've got 1 minute, we can't do it now. And it makes sense to, let's try and do one of these nullcline things together in class on Thursday before we move on. But are there any questions before we wrap things up for today? I apologize again about the change of plans. I would rather be there with all of you. So I hope this wasn't too much of an inconvenience. I apologize, but should be back in class on Thursday, and looking forward to seeing you all on campus. If you do have any questions in the meantime, feel free to let me know. The homework is up, so you can get started on that, and just let me know if you have any questions on the homework. Otherwise, thanks everyone, and I'll see you all on Thursday. If you have some questions, you're welcome to hang around afterwards.